Wildfires destroy approximately 5 million acres of land in the United States each year, consuming everything in their path at a speed of about 1 mile every 4 minutes. These out-of-control combustions are one of nature's fastest chemical reactions. Of course, fast chemical reactions are not always destructive. If we know how to control them, they can be very useful. For example, space travel is made possible by harnessing the tremendous power of the combustion of hydrogen gas and solid rocket fuel. And not all chemical reactions are fast. Rusting of iron can take place over many, many years. Why are some chemical reactions fast and some slow? What factors do these chemical reactions depend on? Can we speed up a slow reaction or slow down a fast one? These are just a few of the questions we'll explore in Chemistry Matters Unit 9, Kinetics and Gases. Welcome to Chemistry Matters Unit 9, Kinetics and Gases, where we'll investigate the effects of molecular motion on the rates of reaction and properties of gases. Most of you probably know that kinetic energy is the energy of motion, so it should be no surprise that kinetics is the study of motion. Specifically in chemistry, kinetics is the study of reaction rates. The rate of a chemical reaction is simply a measure of how fast a product is made or a reactant is consumed. Rates of reaction are expressed as the change in concentration of a reactant or product over a specific period of time. As we learned in Unit 7, molarity is the most common unit of concentration. Units of time depend on the rate of reaction and vary from seconds to minutes to hours. So just like the rate of a moving car usually has units of miles per hour, the rate of a chemical reaction typically has units of molarity per second. Scientists explain different rates of reaction with the collision theory. This theory states that particles must collide in order to react. But not just any type of collision will result in a chemical reaction. In order for a chemical reaction to occur, collisions must occur with enough energy for a reaction. Additionally, collisions must occur with the reactants properly oriented relative to each other. We call collisions that result in a successful reaction effective collisions. Here you see examples of ineffective and effective collisions. In an ineffective collision, there's not enough energy, and the reactants are not properly oriented to each other, so there's no change to the reactants. A successful chemical reaction is kind of like a good game of pool. Imagine you've just set up the pool balls in a perfect triangle, and you're ready to make the break shot. You aim for the ball front and center. If your cue ball hits with the correct orientation and energy, the 15 billiard balls will scatter across the pool table. Some of them will drop into holes. But if the cue ball hits in the wrong place or with low energy, the 15 billiard balls will barely move. To further explore reaction rate, let's go out to our classroom and join our students.
While we don't have as much control over a chemical reaction as we do in a game of pool, we can affect the rate of a reaction by altering the conditions under which it occurs. In order to adjust the rate of reaction, we must first understand the factors that affect rate. Chemists often use an energy diagram to represent a chemical reaction. The energy of the reactants is shown to the left, and the energy of the products is shown to the right. The top of the energy hill in between the reactants and the products represents the activation energy, which is the minimum amount of energy needed for reactants to convert to products. Activation energy supplies the energy needed to break existing bonds in the reactants. We'll explore activation energy further in Unit 10. For now, think of activation energy as a hill the reactants must climb in order to transform into products. if reactants do not collide with enough kinetic energy or activation energy, they won't react to form a product. If, on the other hand, reactants collide with adequate energy to break the existing bonds, a product will form. Based on what you've learned about the collision theory so far, can you think of a way to speed up the reaction?
Couldn't you just give the reaction more energy?
That's right. Particles have to collide with enough energy to react. How could we give a reaction system more energy?
By heating it up?
Good. Heating the reaction would give the reactants more kinetic energy. More kinetic energy means faster movement and more energetic collisions. Does anyone else have any other ideas? Dory?
Since more frequent collisions mean a faster rate of reaction, could you put the reactants into a smaller container so they're more crowded and they collide frequently?
That's a creative idea, Dory. Let's think through a little bit more. Let's say I have a 250 milliliter beaker that's holding 100 milliliters of an aqueous solution. Now, if I were to pour the 100 milliliters into a smaller container, will the components of the mixture be closer together?
No, I guess not.
Good. Why not?
Because you can't squeeze 100 milliliters of a solution into a smaller space.
But if it's a gas, you can. Think about tires. They're filled with high air pressure, right?
Great example.
Yeah, I don't think liquids and solids can be compressed, but I'll bet gases react faster when they're put into a smaller space.
That's absolutely right, Dory. So you weren't incorrect with your suggestion of putting reactants into a smaller container. We just have to clarify that only gases can be compressed into a smaller volume. We'll explore rates of reaction with gases later. Right now, we'll investigate aqueous reactions. There are ways to make reactants dissolve in water collide more frequently. Can anyone think of how we might do that aside from heating the solution? I'll give you a hint. The solution I'm holding contains only a few milligrams of table salt in about 100 milliliters of water. The particles dissolved in the water collide with each other, but probably not very often. Is there anything that we can do to make them collide more frequently?
Add more salt?
That's right. If we add more salt particles, they're more likely to collide with each other the same way you're more likely to bump into somebody in a crowded room. The frequency of collisions will increase as concentration increases, and so will the rate of reaction. So we've come up with two methods to increase the frequency of collisions and therefore the rate of a reaction. Add energy by heating and increase the concentration of the reactants. Those are the two most important ways to increase the rate of reaction. There are a couple more methods that I can think you'll discover if you conduct your own investigation. We're going to investigate the chemical reaction that the ingredients in an Alka-Seltzer tablet undergo when dissolved in water. This is the reaction that occurs inside the stomach when people take Alka-Seltzer for an upset stomach. Alka-Seltzer is a medicine used to neutralize excessive stomach acid. Each tablet contains citric acid and sodium bicarbonate, which is simply the chemical name for baking soda. When a tablet of Alka-Seltzer is dissolved in water, the citric acid and the baking soda react with each other to produce carbon dioxide and sodium citrate. Sodium citrate is a weak base that neutralizes stomach acid. Monitoring the carbon dioxide produced is a good way to follow the rate of this reaction. If we were to conduct this reaction in a closed container, the carbon dioxide generated would create pressure, and you could think of your stomach as a partially closed system. When you take the Alka-Seltzer, as the carbon dioxide gas is formed in your stomach, the pressure builds up, probably causing you to burp. We're going to investigate this reaction using a film canister as our closed reaction vessel. I need everyone to put on their goggles. I have water in this film canister. When I add an Alka-Seltzer tablet and then quickly put the lid on, pressure will build up until
That's scary.
Now, how long do you think it took for the canister lid to pop off?
Just a few seconds.
It didn't take very long at all.
Well, if we measure the time it takes for the lid of the canister to pop off, we'll be able to compare the rate of this reaction under different conditions. The faster the rate of reaction, the faster carbon dioxide will be generated, and the sooner the lid will pop off. So let's get started on this lab. You'll begin by designing an experiment to determine which conditions speed up or slow down the reaction rate.
This is a good time to take a break and let you design your own experiment along with our students. Your objective in this experiment is to determine the set of conditions that gives you the highest rate of reaction. In other words, what conditions cause the lid of the canister to pop off fastest? You've already learned that temperature and concentration are factors that affect the rate of reaction, but there are additional factors that can also affect reaction rate. See if you can determine those factors. Since you're going to design your own experiment, the first thing you'll need to do is to develop a hypothesis that can be tested by experimentation. Once you've generated your hypothesis, sketch a model of what's happening on a molecular level based on that hypothesis. Remember, a model is a simplified representation of a complex system that helps explain a phenomenon. The model should demonstrate the effect that changing conditions have on the reactants and products. Once you've developed your hypothesis in a model, you'll design your own experimental procedure, have it approved by your teacher, and then conduct your experiment. Make sure you include a list of types and quantities of the materials you'll use in your experiment. This will be a step-by-step procedure, including safety precautions, and a data table that will be used to collect observations and measurements. Be sure to collect data in a way that ensures the relationships between your variables will be clearly identified. That's a lot, but you can find a document containing these instructions in the Chemistry Matters Toolkit. When you're done planning your experiment, go to the next video on the Unit 9 playlist, where we'll head back to our classroom to see how our students did with their hypotheses, models, and experimental procedures.